Hello my friends and welcome back to the You Can Do TV channel. Mountain road construction in India, particularly along border areas, involves cutting through hard rock to create essential pathways. These roads are vital for both civilian access and military logistics, especially in remote regions like the Himalayas. Cutting through hard rock requires advanced machinery such as hydraulic rock breakers, excavators, and drilling equipment, alongside controlled blasting techniques. The rugged terrain and unpredictable weather conditions pose significant challenges, demanding precise planning and skilled labor. Border roads are often constructed under the supervision of the Border Roads Organization, which plays a key role in ensuring the infrastructure is resilient and sustainable. The Karada Road Improvement Project, situated in Algeria, addresses the segment connecting the towns of Borj Mira and Karada, covering a distance of 7.6 kilometers. This road is a vital link between the provinces of Bayaya and Sétif and serves as a crucial part of the national road network. Originally constructed by the French in 1865, the road was designed to meet the transportation needs of the time, with a width of only 3.5 to 4 meters. Over the years, the narrow road has become inadequate to handle the growing traffic, especially heavy trucks, and the challenging geographical conditions have exacerbated the situation. The road's layout is particularly dangerous, as it is flanked by steep cliffs on one side and a drop-off into a riverbed, 30 to 50 meters below, on the other. Due to the road's historical importance and its strategic location, the Algerian authorities initiated a project to modernize and expand it. This initiative involved constructing viaducts with steel girders supported by concrete pillars, semi-bridges, box culverts, tunnels, and widening the road. The unique feature of this project is the use of estacat, a special type of pre-stressed beams, which extend the road by 2 to 5 meters in a cantilever fashion over the riverbed. These structures are engineered to blend with the challenging topography, ensuring the road's safety and longevity. One of the most significant challenges faced by the project team was working in the rugged terrain of the Karada Gorge. The natural beauty of the gorge is matched only by its geographical difficulties. The original road, built more than 150 years ago, was constructed with a width that is no longer sufficient for modern traffic, and the number of vehicles using it has increased dramatically over the decades. The 1980s saw the first attempts to improve the road, but by the early 2000s, it became clear that a more comprehensive solution was needed. The project involved extensive studies to ensure its feasibility and safety, including geological, topographical, and terrain analyses. These studies highlighted the need to modify the entire route and redefine the construction methodology to provide a more solid foundation. The aim was to create a safer, wider road that could accommodate modern traffic demands, particularly the increasing number of heavy trucks using the route. The newly designed project features a total length of 7.6 kilometers, including 3 bridges, each measuring between 30 and 60 meters. The most complex part of the construction involved the use of the estacat system, which required building special retaining walls and supporting structures. These walls and structures had to be designed to withstand the weight of the extended road while ensuring stability in the rocky and unstable soil conditions. The construction process itself posed numerous challenges. For instance, installing large beams weighing 160 tons required the use of heavy-duty cranes, which proved difficult due to the narrowness of the existing road. The project team overcame this by assembling the beams on site and sliding them into position using specially designed equipment. The entire operation was carried out with great care to avoid accidents, and the engineers involved in the project held numerous meetings to refine the methodology and ensure the safety of both workers and future road users. Throughout the construction, the team encountered frequent difficulties, such as the sliding of soil and rocks during excavation. These unexpected events forced the project team to continuously adapt their plans and develop new solutions. For example, when it became clear that the planned foundation depth of 3 meters was insufficient, the team had to dig to a depth of 6 meters and reinforce the structure with micropiles to ensure stability. Despite these challenges, the project proceeded with remarkable success. The use of modern engineering techniques and technologies played a crucial role in overcoming the difficulties presented by the terrain. The project also emphasized the importance of worker safety, with significant investments made in health and safety measures to protect the team from accidents. As of now, no major accidents have occurred, a testament to the careful planning and execution of the work. The Karada Road project is not only a significant achievement in terms of engineering but also a source of pride for the Algerian people. The road will provide a safer, more efficient route for travelers and contribute to the economic development of the region. The project's success is due in large part to the collaboration between Algerian and Turkish engineers, who have worked together to push the limits of engineering and deliver a practical, long-lasting solution. The super project on the cliff in Chongqing is an ambitious architectural marvel that integrates seamlessly with the surrounding natural landscape. Located in southwestern China, the project directly surrounds a mountain, creating a stunning blend of urban design and nature. The development consists of high-rise buildings and structures built along the steep cliffside, offering breathtaking views of the city and the Yangtze River. The engineering challenges are significant, requiring innovative techniques to ensure stability and safety while preserving the mountain's natural beauty. This project exemplifies Chongqing's rapid urban development, showcasing its ability to merge nature with modern infrastructure. It is both a tourist attraction and a symbol of China's advancement in sustainable, eco-friendly construction methods in difficult terrain. The railway line connecting Koblenz to Pau crosses the Moselle River at the community of Neath, where it enters the Petersburg Tunnel. Current regulations for double-track railway lines necessitate a minimum distance of 4 meters between the track axes. To comply with these standards, the Petersburg Tunnel requires enlargement. The installation of technical facilities begins after the formation and asphalting of an earth bank at the site. The only significant disruption to railway services occurs during a planned 4-week closure of the tunnel, during which the double-track line is temporarily reduced to a single track. Marty also constructs a 470-meter-long protection tunnel made from steel and wood, which ensures the safety of both staff and rail traffic. Once the protection measures are in place, additional work is conducted to reinforce slopes and prevent rockfall, ensuring the safe continuation of railway operations during the construction process. Next, the tunnel enlargement system is installed at the south portal. This system, developed by Marty Technic, is a specialized platform that houses all the equipment necessary for the tunnel driving work. It also provides a stable working surface for the crew. After its installation and rigorous testing, the fully assembled system is positioned at the tunnel entrance with the help of a massive crane. The excavation of the tunnel is done in a cyclic process. The initial step involves blasting the rock, followed by the removal of loose debris with hydraulic hammers. The tunnel's arch is then reinforced using sprayed concrete. After the material has been cleared away, the crew installs a first layer of steel reinforcement mesh, supported by lattice girders. This is followed by another layer of sprayed concrete, which helps stabilize the structure. The construction team then bolts the structure to the rock to further secure it. A second layer of reinforcement mesh completes the cycle. To prepare for blasting, a drill rig is used to bore holes into the rock. Marty's experts carefully place and fire the explosives after ensuring the area is safe. Once the railway company's safety officer has inspected and cleared the tunnel, blasting is initiated. Despite the active construction work, trains continue to pass through the tunnel every 8 minutes, underscoring the precision and coordination required to maintain rail operations. Following each blast, loose rock is cleared away using hydraulic hammers, and the debris is transported to the sides for temporary storage before being removed from the site by truck. The construction process for securing a tunnel arch begins with the application of a first sprayed concrete lining, which serves as an initial layer of stabilization. Following this, reinforcement meshes are installed, and lattice girders are precisely positioned to support the structure and the surrounding rock. Despite challenging conditions, the installation of these girders is performed with centimeter-level precision by the dedicated crew. Once the lattice girders are in place, a thicker layer of sprayed concrete is applied to the tunnel. This first thick concrete layer serves as the primary support, followed by a second sprayed concrete lining applied to the previously secured sections. In parallel, drill rigs are deployed to drill anchor holes, which can be up to 5 meters deep. These anchors ensure a secure attachment of the sprayed concrete lining to the rock, further stabilizing the tunnel structure. As the excavation work progresses toward the northern portal of the tunnel enlargement system moves back toward the southern portal. During this return journey, abutments are constructed at the base of the arch. These abutments will later support the final inner concrete lining. Simultaneously, the installation of critical equipment begins, including the formwork carriage, reinforcement carriage, transport carriage, and ceiling carriages. Once the abutments are completed and the tunnel enlargement system reaches the southern portal, the first phase of the inner lining construction is complete. To avoid disruptions to regular rail services, the tunnel enlargement system is replaced at night with the newly assembled formwork carriage components. The concreting of the final arch lining then commences. The construction cycle starts at the northern portal, where the transport carriage delivers prefabricated reinforcement components to the worksite. There, workers manually connect the steel arches and meshes to form a load-bearing structure. Despite the physically demanding conditions, the installation is carried out with precision. Next, the formwork carriage is positioned with centimeter accuracy, and its hydraulic elements are adjusted and sealed against the tunnel arch. The system must be both flexible and robust to withstand the immense pressure exerted by the liquid concrete. The concrete is applied symmetrically on both sides to prevent any shifting of the formwork under the high pressure. Inspection doors allow for monitoring the concrete's distribution during application. Sealing carriages ensure that the concrete cures properly by preventing rapid moisture or thermal loss, reducing the risk of cracks. Once the inner concrete lining reaches the southern portal, the tunnel enlargement phase is considered complete, and the portal structures are finished using the cut and cover method. Over the past decade, China's asphalt paving technology has undergone remarkable advancements, driven by the nation's rapid infrastructure development and the increasing need for high-quality roadways. 10 years ago, the country's asphalt paving techniques were primarily centered on conventional hot mix asphalt (HMA) processes, which, although widely used globally, had certain limitations in terms of environmental impact, durability, and cost efficiency. Over the years, however, China has made significant strides in adopting innovative technologies such as warm mix asphalt (WMA), reclaimed asphalt pavement (RAP), and intelligent paving systems, which have contributed to more sustainable and efficient road construction. Asphalt paving technology in China 10 years ago. A decade ago, China's asphalt paving technology was largely characterized by the use of traditional HMA. This technique involved heating asphalt to temperatures between 150 degrees Celsius and 180 degrees Celsius to make it workable for paving. While effective, this process consumed large amounts of energy and released significant emissions, contributing to environmental degradation. Furthermore, road lifespans averaged 10 to 15 years, depending on traffic volumes and climate conditions, and repairs were frequent. In 2014, China produced around 500 million tons of asphalt annually for its road network, which was growing at a rapid pace due to massive infrastructure projects. However, quality control was still an issue in some regions, as the rush to build often compromised the durability of roads. There was also limited use of recycled materials, with only around 10% of asphalt pavement being recycled. Recent developments in China's asphalt paving technology. In the last 10 years, China has taken significant steps to modernize its asphalt paving technology, focusing on sustainability, efficiency, and longevity. One of the most notable changes has been the widespread adoption of warm mix asphalt, WMA. WMA allows asphalt to be mixed and applied at temperatures ranging from 100 degrees Celsius to 140 degrees Celsius, reducing energy consumption by up to 30% and cutting greenhouse gas emissions by approximately 30 to 40% compared to traditional HMA. This shift has been driven by both environmental regulations and cost considerations, with WMA becoming the standard for many major road projects. Another critical advancement has been the increased use of reclaimed asphalt pavement, RAP. In 2022, around 35% of asphalt used in China's paving projects was made from recycled materials, a significant increase from 10% in 2014. The use of RAP not only reduces the need for new raw materials but also lowers construction costs by up to 20%. Some projects have even achieved RAP usage rates of 50 to 60% without compromising the quality or longevity of the roads. China has also invested in intelligent paving systems, which use sensors and GPS technology to ensure precise control over asphalt thickness, compaction, and temperature. These systems have improved the overall quality of road surfaces, reducing the frequency of repairs and extending the lifespan of highways to 20 to 30 years in some cases. Additionally, the use of polymer-modified asphalt has increased, further enhancing the durability and flexibility of roads in extreme weather conditions. The milling and paving process for asphalt surfaces like parking lots, streets, and driveways is a complex operation that requires precision and expertise. Once the site is prepared, the next step is to mill the existing asphalt surface. A milling machine grinds away the old, damaged asphalt at a predetermined depth. The milled material, or millings, is loaded into dump trucks and hauled away for proper disposal or recycling. Milling ensures that the surface is smooth and consistent, allowing for better adhesion and a more even finish when the new asphalt is applied. High-quality milling equipment is essential, as it allows for precise depth control and ensures the surface is uniformly prepared for the next phase. Surface cleaning and preparation. After milling, the surface must be thoroughly cleaned to ensure proper adhesion for the new layer of asphalt. Any remaining debris or dust can interfere with the bonding process between the old and new asphalt layers. This cleaning is typically done with a team dedicated to ensuring that no contaminants remain, as even small particles can lead to future pavement failures, reducing the longevity of the newly paved surface. Application of tack coat. Once the surface is clean, a tack coat, which is a thin layer of a commercial-grade concentrated adhesive, is applied. This tack coat serves as a bonding agent between the milled surface and the new asphalt overlay. It is a critical step in preventing delamination, which can cause the layers to separate over time and lead to cracking and potholes. The tack coat also improves the durability of the pavement by allowing for a stronger bond between the different asphalt layers, significantly extending the lifespan of the paved surface. Laying the asphalt. With the surface prepped, the paving process can begin. The asphalt mix used is carefully designed to meet the specific requirements of the project. It is critical to use an asphalt mix with the right aggregate size and oil content to ensure that the final product is not only aesthetically pleasing but also capable of withstanding years of use and environmental wear. Modern paving machines are equipped with advanced technology, including automatic depth sensors, sonic rate sensors, and paving joint sensors. These tools allow the paving crew to ensure that the asphalt is laid down evenly, with the correct thickness and seamless transitions between joints. Dump trucks deliver the hot asphalt mix to the site, where it is unloaded into the paving machine. The paver then spreads the asphalt evenly over the surface, and the crew manually works the edges to ensure a sharp, clean finish. As the paving machine moves, it carefully maintains consistent temperature and density, which is essential for the quality and longevity of the pavement. Compaction process. One of the most critical parts of the paving process is compaction. After the asphalt is laid down, it needs to be compacted while it is still hot. This process removes any air pockets and ensures that the asphalt is densely packed, which is essential for it to withstand heavy loads and prevent cracking. A vibratory roller is typically used for compaction. This machine passes over the asphalt several times, following a specific roll pattern at precise angles to ensure maximum density. The timing, pace, and vibration frequency are all carefully controlled, as improper compaction can lead to weak spots in the asphalt, causing premature failure, especially in regions with frequent freeze-thaw cycles. Proper compaction also plays a critical role in the ability of the asphalt to support vehicle traffic. Insufficient compaction can result in depressions or ruts forming under the weight of vehicles, while overcompaction can weaken the structure of the asphalt. Final touches and striping. Once the asphalt is laid and compacted, the final step involves the finishing touches. This includes painting the necessary markings, such as parking lines, traffic arrows, and any other designs required for the surface. Striping is a meticulous process that requires precision, as the quality of the lines directly impacts the functionality of the parking lot or road. At this stage, contractors often use highly advanced striping machines to ensure that the lines are straight, evenly spaced, and durable. The paint used is designed to withstand weather conditions and heavy traffic, ensuring it remains visible and intact for years. Post-paving maintenance and inspection. Even after the project is complete, many paving contractors, like SPS mentioned in the transcript, go the extra mile by inspecting the area for any remaining debris or imperfections. They may perform additional cleaning, such as sweeping or blowing away any stray particles, ensuring the site looks pristine.